Hello, so today at Joining's Community, we have Dr. Barbara Liskov. She's an institute professor and the head of programming methodology group at MIT's Computer Science and Artificial Intelligence Laboratory. She has made pioneering contributions to programming languages and distributed computing. Some of her many achievements include the introduction of abstract data, um, types and the accompanying principle of data abstraction, along with the Liskov substitution principle. We are immensely grateful to have you here today, Dr. Liskov. Would you be able to start us off on expanding on your educational and professional journey that's led you to where you are right now?
Sure. I grew up in San Francisco. I went to public school, and then I went to college at UC Berkeley, and I majored in math. And then I graduated in 1961. And I decided when I graduated that I wasn't ready to go on to grad school. I'd been thinking of grad school in math. And so I went to look for a job, and I was looking for a job that took advantage of my math background. And I didn't find anything interesting that was math, but I was offered a job as a programmer, even though I didn't even know computers existed and obviously had no training. But this was not unusual at the time because there were no computer science undergraduate programs. And so companies who needed programmers had to take a chance on someone like me who didn't have any background, but maybe could do the work. And my first day on the job, I was handed a Fortran manual and asked to write a little program. And I discovered a field that I really loved. And that was also a very good match with my capabilities. So I worked at that first job for a year. And then I switched and went to work at Harvard on their language translation project. And although I made this switch because I was living in Cambridge and it was a much better commute, it turned out to be a very good move because at Harvard, I was maintaining a large program written in assembler. I think it was a 7094 they were running. And my job was to maintain this program. And so because it was written in assembler, I began to see what was going on under the covers and developed a much better understanding of what was happening in the computer itself, not the internals of the computer, but the interface it provided to programmers. And also I began to understand what the compiler had been doing. This is now the fall of 1962. I graduated in 1961. So my first year was at MITRE, my second year was at Harvard. And in that fall, I applied to graduate school. I decided that I was entirely self-taught and probably would be smart to get some training. And so I went to Stanford in the fall of 1963. And I don't remember how many new students came in that year, but it was a very small number, maybe 5. It wasn't yet a department. There was a program in computer science joint between math and EE. And at Stanford, I had a great time. I worked with John McCarthy. He was one of the founders of AI. And my thesis was on a program to play chess endgames. And chess was a very challenging problem at the time because computers were very small and slow. And in order to make progress in the way that the chess programs worked is they did search. And you couldn't search much when you had such a small, slow computer. So you had to come up with clever heuristics. And I was working on chess endgames, one of the parts of chess where the heuristics were different than other parts. And so that was my thesis. I was at Stanford for 5 years. And when I graduated in 1968, I would have liked to have gotten a faculty position, but I didn't get any good offers. And so I decided to go back to the MITRE Corporation, which is where I had worked originally. Only this time I was a researcher rather than a programmer. And I also was switching out of AI into computer systems. I had decided partway through my Stanford career that I wanted to make that change. I didn't do it while I was at Stanford. I pursued my thesis in AI because that's where I had been working, but I knew I wanted to make the change when I got out. And it turned out to be a really good move because at MITRE, I could make that switch without all the extra work that was involved in being a faculty member. I didn't have to worry about teaching courses. I didn't have students I had to advise, and all the other kinds of extra work that go on at an educational institution. And also, I had a lot of autonomy. They handed me a project when I arrived, a very interesting systems project. And that took the first couple of years. And then when that was completing, they handed me another project, a fascinating project about what was called the software crisis, which had to do with the fact that at that time, people didn't know how to build software systems that worked. And it was very common in those days to pick up the newspaper and see an article about some company that had spent millions of dollars and hundreds of man years. They were always man years in those days. And in the end, they had to throw the software away because it just didn't work. And this got me into a field called program methodology, where people were trying to figure out how to solve this problem. How can we figure out how do we design programs that work? How do we organize programs that work? Um, and since it was a field it was a new field for me. Of course, I read all the literature I could get my hands on. And anyway, so that was a very interesting field. And then I got an offer to move to MIT. So what happened in those 4 years that I was at MITRE was, of course, I had moved from AI into systems, but also Title IX was about to be passed. And Title IX was about athletics, access to athletics for women, but turned out to have a big impact on opening academic positions for women. And at that point, a few universities were, they could see it coming, and they decided they should start looking for women faculty. And so MIT was one of those places. And the way they knew about me was because I had written a paper on my first project, and it was a prize paper at the Top Systems Conference. So at this conference, when I gave my talk, the chair of the session was a professor at MIT, and there were other MIT faculty in the audience. And so as a result, I was asked to apply to MIT, and I did. And I moved there in the fall of 1972. And in 1972, I joined the EE department. There was no computer science yet. And I was the first woman in the department in computer science. And at that point, there were 10 women on the faculty out of a faculty of nearly 1,000. So it gives you an idea of what things were like in academic positions at that point in time. And it was a perfect time for me to move because I had found this area that I was absolutely passionate about, and I knew what research I wanted to do. That's the glory of an academic position. You get to choose your own projects. Of course, it's also the problem. You have to figure out what those projects are. You have to get funding for them and so on. So in the first semester when I was at MIT, I came up with the idea of abstract data types. I could see suddenly that what people were talking about as the modules that should make up programs could be thought of as abstract data types, sort of things, entities with hidden information inside and a bunch of operations that allowed you to interact with the objects that were associated with them. And that's when my career really took off. So that's sort of how I got into the field and how I got started.
Thank you so much for sharing that. So, I know you mentioned that during your time at MITRES, you had a lot of independent projects, and then when you moved to MIT, you were basically going through abstract data types. Was there a specific highlight in your career or an impactful project or moment where you felt like your contributions significantly influenced the field that you're in?
When I came up with the idea of abstract data types, I knew immediately that this was a very important idea. And I wrote a paper on it with I had a co-author, a person who was a student at MIT at the time, and he had similar ideas. So we decided to flesh out this idea and think about what it meant for a programming language to support this idea. And the paper that we wrote in the summer of 1973. So this is 9 months after I arrived at MIT. It wasn't published for another year, but the reception for this paper was huge because it was clearly the idea that people were looking for. And so, yeah, I mean, that was an amazing moment when I had that idea and I could see how important it was and I could see where we were going to go with it and all the work that had to be done next. It was great.
Thank you so much for that insights and congratulations. That's huge. And I think moving from that, like what are some of the most exciting advances in your field that either you've contributed to or you've just seen the progression of throughout your career?
Well, so I consider myself, as I said, I moved out of AI.
Yeah.
So I have not worked in AI since I was at Stanford. And so I have been focused on the systems area. And it's a fascinating area. You know, first I started with programming methodology, then I worked in programming languages, then I started working in distributed computing, which was at the time I started, there were just a few universities and research institutes that had access to the internet, and people were trying to figure out, you know, what do you do with this internet? And I jumped into that field when I finished the project on Clue, which was the programming language that I developed to work out how a programming language could support data abstraction. And so, you know, I don't know that I can really answer the question in general. There were many interesting things going on in systems.
Mm.
Um, for my own work, um, when I think back on my career, I sort of identify four sort of key things. I mean, I did lots of stuff and I kept changing areas, but I was always in the systems area. So there was data abstraction and Clue. And then I switched into distributed systems, distributed computing. And my first project there was also a programming language that would allow you to write programs that had components at many different computers connected by networks. But I also got interested in the problem of memory and really basically what is the cloud and how those systems would work. And with one of my students, we came up with something we called U-stamp replication, which ensured that the data you entrusted to the cloud would be consistent with the past history, would work properly in spite of the fact that many people were trying to use it, and would continue to provide service even though machines might fail and so forth. And then much later, a couple of maybe 20 years later, with another student, I worked on what's called Byzantine fault tolerance, which is the same thing, except that now we worry about what happens when malicious hackers get into your computer and cause it to be corrupted and so forth. And how do you still continue to have a good service in spite of those things? So there were those, that was one direction I went in. But I always was interested in program methodology, and the Liskov substitution principle was something I came up with in the 80s when I was asked to give a talk at UPSLA, which was the big object-oriented programming conference. And I think this was the second year that UPSLA was in existence. And that caused me to go and look at the other part of object-oriented programming, which was coming out of Smalltalk. This was work done by Alan Kay and Del Goldberg, based on an earlier programming language called Simula. And when I started to look at the literature coming out of that part of the world, I discovered that they were talking about something they call type hierarchy, and they didn't know what it meant. And since I had been thinking about data abstraction from the point of view of, I thought about it from the point of view of specification. So I would think about what is the meaning of this module? And separate from that, how do you implement it? And then how do you reason about the correctness of that implementation and so forth? I could see that by thinking about this in the terms of specifications, that you can come up with a definition that defined how subtypes had to behave in order for type hierarchy to make sense. And I talked about that in my UPSLA talk, and that's what came to be called the Liskov substitution principle. And of course, I didn't, say I'm going to tell you today about the Liskov substitution principle. What happened was I gave that talk, I think, in 1987. And sometime in the early 90s, maybe 1992 or so, I got an email from someone saying, can you tell me if this is a correct interpretation of the Liskov substitution principle? And that's when I discovered that there was this name and that there was a huge group of people that were using this and interested in it and wanting to understand it. And slightly later, Jeanette Wing, who had been had been a student at MIT, and she did her, I think she did her bachelor's thesis with me, and then she switched and worked with a colleague of mine for her PhD thesis. Anyway, Jeanette thought that it would be a good idea if we could really pin down the exact definition of what the Liskov substitution principle was. And so we worked together and we wrote a paper that was published in the 90s that really contains the definitive definition of what it is. So those are the four things I look back on, but there was lots of interesting work going on, and it was just, I was having a lovely time, and I had great students and I had great colleagues, and I enjoyed the teaching. I mean, it was really just lovely.
Yeah. I think going back to like very early on in your career, during your undergraduate career at Berkeley, I know you mentioned that you were majoring in mathematics, is that correct?
Yeah.
Was there a specific point in your life where you knew you wanted to pursue a career in STEM? Was that during your high school when you first learned that you enjoyed mathematics, or throughout your time in college?
No, I think I wasn't thinking about careers,
Mm,
but what I was thinking about was what was interesting. And I was always interested in math and science. And I felt in my high school that this was not what girls were supposed to be doing. But I just ignored this and took the classes I was interested in. At that time, they didn't have AP courses. What they had was college prep. And the most advanced math course they had was a pre-calculus, which was, I think, I'm not sure how many students took that class, but it was a very small number of me and a bunch of boys, because there were really very few girls doing what I was doing. And at Berkeley, there were almost no women majoring in math.
wow. Um, I guess jumping off of that, um, is there anything you'd like to say about like the change in representation or the representation of women in STEM in your respective field throughout your career?
Well, as I said, when I got to MIT, there were 10 women on the faculty.
Right.
And I don't remember how many female students there were, but the numbers started to increase. And after a while, the percentage of women faculty got up to about 10%, and then it stalled.
Mm.
And the students gradually increased and increased. I remember at some point must have been in the 80s, it began to feel more, MIT, which is an engineering school, began to feel a bit more like what I had experienced at Berkeley, in the sense that there were many more students, female students, and it was making a difference in how the place felt.
Yeah.
Um, so it was sort of a gradual improvement. And today at MIT, I'm a little out of the loop, because I've retired. I used to know all the statistics and so forth, but the last time I checked, MIT is about 50-50 now as far as number of students is concerned. And in the major, the last time I checked, it was over 30%. So it was really, growing. But I think that nationally, this is true at some of the top schools, but not across the board. And so the percentage of women in computer science, which is what determines how many we're likely to have at graduate school, is still, I think, around 20%. So it's not grown as much as we might like to see. And a lot of the problems are coming from, they're not coming from the colleges, they're coming from K through 12, they're coming from um, our way our society works. And in fact, actually, it's pretty appalling if you go online and see the objectification of women. I think it's gotten worse rather than better. So it's tough for girls to come to grips with all this.
Could you describe any challenges that you might have faced as a woman in STEM and how you overcame it? I know you mentioned there are very few women who majored in mathematics at Berkeley, and you were one of 10 faculty who are women at your time at MIT, or at the beginning of MIT.
Yeah, I did not have the kinds of experiences that some women report on.
Mm.
And I'm not sure why this is true. I mean, why did I manage to avoid them and other people didn't? I do think looking back at MIT, I had people looking out for me, although I didn't really understand that this was happening. But the person who hired me was watching. They were careful to make sure I got the right assignments, that they were helping. They helped me when I had initially been put in the wrong floor of the building and I got moved. Um, Stuff like that. I'm not talking about awful things where some awful things happen, where women were propositioned, or, the stories about um, somebody needs to go and get the coffee. So the woman in the room is told, go get the coffee, that kind of stuff. I'm talking about more making sure that young faculty have the right assignments and that the right kinds of resources are moving in their direction. People were watching out for me. And it's very important that, and I know at MIT, we try very hard to make sure in my department that the young faculty have the resources they need and they're teaching the right courses and they have somebody to talk to if there's problems. And so
Right.
that kind of stuff is very important.
Yeah, and could you expand on some of the measures that MIT or during your career, the people around you and your particular institution and organization that you were working on, what they did in particular, if they did at all, to create a more inclusive environment for women entering the STEM field?
Yeah, that one, I don't know that I can answer that question. It sort of came along one person at a time.
Mm.
So, I was the first woman, and gradually we got a few more,
Right.
and some of them succeeded. And as you get more population, then it's easier. Yeah, the women did used to meet for lunch periodically, so at least you could, see each other.
Yeah.
But in the early days, in my department, there was me and Millie Dresselhaus, a very renowned double E person. And then everybody else was from a different department. So it was just gradual improvement, basically coming from the top. So, the president of the institute had decided we had to do this. And so then, you put in place, you make sure that there is some sort of fairness in how people are hired, and you make sure that people are treated appropriately so that they can succeed and stuff like that.
Right. I guess with that increasing number of women in faculty, and I know you mentioned there was a period where the number of women at MIT had sort of halted at 20%. Um, Forgive me if I'm stating anything incorrectly. Did you see any change in sort of the innovation and progression of like STEAM fields? And overall, do you have any thoughts on how representation of women in STEAM, impact inclusion and innovation in the progression of STEM?
So the percentage of women faculty sort of stalled at 10%
10%. Wow.
for
Okay.
quite a while, maybe until around 1990, and then with further effort, things started to move up. I think that um, it's, what people say is that you want the best people, and if you choose the best people from half the population, then you're not going to get all the best people. I think the thing that I noticed was that the women we hired were doing really well. So, we wanted people who do really well. And you didn't see, oh, the men are doing so much better than the women. No, the women were doing really well. And so as you see, as the larger population notices that the women are actually doing very well, it makes them more receptive to uh, broadening the pool and so forth. Now, I've been talking about women. It's a much harder problem for underrepresented minorities.
Yeah.
And, their progress is being made, but it's much slower and much more difficult. And that has to do with the class society that we have in the United States, and the fact that if you don't have enough money, you don't necessarily get a good education before you ever get to college. And then, it makes it very hard for you. It really astounds me how people don't understand what affirmative action is all about. And, but anyway, that's a topic for another day. But yeah.
Thank you for sharing that. I know earlier on in the interview you mentioned that some of the hindrances of women going into graduate school, and also like higher positions of power in STEM, are from like their experiences from K through 12. And I was wondering if you could, expand on how you think these like societal constraints sort of shape like women's abilities, or not women's abilities, but perceptions of how well they can do within the STEM field.
Um, I guess what I can say is that I know that most places have outreach programs.
Mhm.
These outreach programs are important because they give people a chance to see what this future could be like. Where they wouldn't necessarily have that information if they're just a student in a regular school. So, uh, you know, those programs are important. And also, I think support for people when they arrive at the school can be very important, especially in the case of underrepresented minorities where uh, their background might need a little bit of boosting from, uh, to give them a chance to overcome whatever deficiencies there were in their earlier education. Um, I'm not sure that answered your question, but
No, that's all right. If you'd like, would you expand on like other steps that institutions and organizations can take to make a more inclusive environment for underrepresented groups and women in STEM? I
um,
mentioned outreach groups, so just like expanding on that or any other initiatives.
yeah, no, all I'm saying is that um, we need, uh, in order for us to make progress, we need the, these groups to go to college and work in these fields. And so programs that, uh, and these programs are all over the place. They could be, stuff like you're doing, or somebody going to talk to groups of kids in elementary school or middle school or whatever. MIT, I know, has some summer programs where students can come and work at MIT and learn about electrical engineering or some science or something like that. Those are very useful. All of these programs, if everybody does their part, they help to increase the pool. That's what's
Thank you for sharing that. And sort of going back to your career, and sort of the young scientists who are watching this video who are interested in your line of work, what is some advice that you'd recommend that they do in their career and journey to be a part of your field?
um, Well, get as good an education as you can. Don't uh, let the fact that people might think that what you're doing isn't what you should be doing uh, get in your way. Follow the path that makes sense for you. And I don't, that's, sort of what I think you have to do. You just take advantage of the opportunities, pay attention to what you enjoy. Don't let yourself be deflected to doing what somebody else thinks you should be doing. Um,
Yeah, and then if you had the option to talk to your younger self, what advice would you give her and why?
Somehow or other, looking back, I feel like I made the right steps.
Yeah,
And I don't know what it was that enabled me to do that. It could have been my parents. I did have parents who wanted me to succeed academically. But when I was a teenager, the idea was that women were going to, they went to college to find a husband and then they were supposed to, not work and raise a family. And my father had me advised me to take a typing class when I was in high school. I spent one of my classes one semester. I took a typing class because, you know, supposing I never got married or something happened to my husband, then I could, support myself. And the jobs that were open to women at that point were secretarial or teaching. Those were sort of the accepted jobs. So it's not like my parents were, uh, you know, out there sort of ahead of the times, talking to me about how I could have a career. But on the other hand, they did emphasize, hard work and doing well in school. And definitely I was going to college. And I'm sure that helped, and they were supportive. So that definitely makes a big difference what parents do.
yeah. And I guess branching off of that, were there any mentors in your life or support networks that played a significant role in your career? I know you were pretty much a pioneer of, abstract data types and the Liskov principle, but is there anyone in particular or groups in particular that helped you be where you are right now?
So it wasn't that I had somebody who was working with me and suggesting research directions.
Mm.
That was all self-driven. But what there was this stuff going on in the background that, helped me uh, make progress um, just by having my back, just by looking out for me, making sure that bad things weren't happening. That was what I experienced. That kind of help. That kind of help was very important. I mean, in fact, that my idea about what it means to be a mentor for a faculty member is you don't tell them what to do. You absolutely leave them completely alone because they need to develop their own ideas. But this is exactly what you do. You make sure their teaching assignments are right. You help them solve problems about um, getting money to support their work and stuff like that. It's exactly what I got. I was just sort of so naive that I didn't even understand this stuff was happening. But looking back, I could see it was happening.
Yeah, that's wonderful. And I guess to conclude this interview, I have one last question for you, which sort of ties into like the larger idea of my project, which is how do you think storytelling or sharing personal experiences can benefit and inspire future generations of people interested in pursuing a STEM career?
Well, what's interesting is that I didn't pay any attention to these stories.
Mm.
But I can see that these stories make a big difference to lots of people because I do give a lot of talks like this. And I see how uh, it's especially the women who react to it, but actually all the young students react to it. It just helps them to see the story. And so I'm happy to tell my story.
Well, thank you so much for being here and telling your story. It was such an honor to have you here, Dr. Liskov. Thank you so much.
Oh, you're welcome. And I'll look forward to seeing the video when you have it ready.